Good morning and welcome back to Chapter 1. This time we're going to be looking at Section 2, and this section's on functions and their properties. So, like the last section, there should be a lot of stuff that, for the most part, is review. Again, there might be a couple little things here and there, maybe a couple vocab words that are different that we know the definition, we just don't know the word. But for the most part, it should be review, which is kind of nice because there's a lot of stuff in here. Again, it's not particularly new, but there's just a lot of it. So let's start taking a look. Our learning targets for the day. We're going to be able to identify functions, like what is a function, what isn't a function. Find the domain and range of functions. Determine discontinuity and whether it is removable or non-removable. Find local maxima and extrema and determine intervals of increasing and decreasing. Determine boundedness. So, first thing we're looking at is the definition of function and function notation. So a function is something that it's a relation where each input goes to exactly one output. So when you know what goes, if you know what's going in, you know exactly what's going to be coming out of it. In our general notation, the function f of x equals something. F of x is y. X is the input. F of x, being y, is the output. So what this means is that for every x value, you have exactly one y value. The input, the x, is called the independent variable, and the output, the y, is called the dependent variable because it depends on what you put in for x. So what would a function look like? A function could look like y equals x squared. We have a parabola shape. We can tell that it's a function by doing what's called the vertical line test. Each vertical line that we could draw will only touch the graph in at most one space. It's a function. For every x value, say this x value, there's exactly one y value. Something that would not be a function could be if we had a parabola on its side. In this case, a vertical line hits in two places. That's not a function because this x value gets us two different y values. That makes it not a function. Circles are not functions. That doesn't mean that they aren't graphs, so we can have equations and everything like that for them, but it's not what's called a function. The domain and range. The domain is everything that x can equal. It's what we can put into the function. Generally speaking, in a purely algebraic, like equation sense, generally speaking, the domain is going to be all reals, except we can't have 0 in the denominator. Anything underneath a square root has to be positive, so we can't have a negative under a square root. And inside of a log, the logs have to be greater than 0, so we can't have 0 or a negative inside of a log. So those are the things that can't happen. So how would we be able to tell a domain? Well, if we had y equals 1 over x plus 3, we just know that this x plus 3 can't equal 0, so that means that x can't equal negative 3. Underneath the square root, let's say we have y equals the square root of 4x plus 7. Well, we know that 4x plus 7 has to be greater than or equal to 0. Then we can subtract the 7. So 4x is greater than or equal to negative 7. X is greater than or equal to negative 7/4. That's the domain. Log is going to be basically the same, except we don't have the or equal to. The log of well, we have 4x plus 7. Let's do 12x. The stuff inside the log, 12x, has to be greater than 0, which we can divide, so x has to be greater than 0. So that's the range. It's it's all reals except we can't have 0 in a denominator, you can't have a negative underneath the square root, and stuff inside of a log has to be positive. Now there are weird things that can happen there. We could have something like y equals e to the 1 over x, where the denominator is in an exponent. So we do need to make sure we're paying attention to that stuff. Now, so this is for when it is just an equation. If this is something that's situational, that may limit the domain. If we're looking at, and by limit, it's like chances are it'll be greater than 0. Because if we're dealing with like time, we're not going to go into negative time. If we're talking about the temperature of Stanwood as the input, the domain's not going to be all real numbers so much. It's going to be like negative 20 degrees Fahrenheit to 120 degrees Fahrenheit. We don't have to worry about the stuff beyond that because it doesn't happen. So there are things that can limit the domain that are situational. And then the range is everything that y, or f of x, can equal. For the range, at this point, there's not much you can do other than graphing it, looking at what the y values are, and things like that. We do have ways of finding these things, but it requires calculus, so we'll get to those next year. But right now, to find the range, you could graph it. You can think about what the equation looks like, and we'll get to that a little bit more later. But if we have, say, a parabola, the range will be greater than or equal to this y value. If we had a cubic, the range is going to be all reals because it's just going to keep going in both directions. So knowing what it is you're looking for, graphing helps that a lot. Continuity. Continuity is going to be a topic that is slightly new, but it's also a topic that kind of makes sense as far as continuous goes. So what continuity is continuity is a continuous function. And continuous just means that there are no gaps in it, there's no breaks, there's no holes, there's nothing. Like, it is one long string of points with no break. So we do have some discontinuities though. We have removable discontinuity. What a removable discontinuity is when you have a graph and you have a hole in the graph, like that. That's a removable discontinuity. Or maybe you have a hole in the graph and the point is just somewhere else. Also, a removable discontinuity. We have jump discontinuities. A jump discontinuity is when you've got a graph going there and then it jumps to some other place on the graph. So with a jump continuity, there's a gap here. With a removable discontinuity, there's not a gap, we're just missing a point. And the last piece is an infinite discontinuity. An infinite discontinuity happens when we have asymptotes. Could be like that. Could be like that. But Either way, there's an asymptote, so it's not going to be continuous, and it's going to go to infinity at that point, or negative infinity. So the asymptotes give us infinite discontinuities. Gaps in our graph give us jump discontinuities, and holes are removable discontinuities. Increasing and decreasing functions. These have definitions. It's increasing if when you increase x, the f of x also increases. Increase means it's going up, has a positive slope. So if we had an increasing function, y equals x cubed like that is increasing because it's always going up. X equals y squared is increasing from 0 to infinity. It's increasing. It's decreasing from negative infinity to 0. Decreasing just means it's going down. So we could have something like that. Is going to be decreasing because it's going down. Again, the quadratic y equals x squared is decreasing from negative infinity to 0. And notice I have parentheses around the 0 on both of these bottom ones instead of a square bracket, meaning it could equal 0. That's because at 0, it's neither increasing nor decreasing. It is constant. Now, when it's constant at a point, that's not as exciting, but it could just be a horizontal line or a horizontal line segment. So we could actually have a graph that looks like this. Let's say that's 3 and that's 1. So it's increasing because it's going up as we're reading from left to right, has that positive slope. It's increasing from negative infinity to negative 3. It's constant from negative 3 to positive 1. And then it's decreasing from positive 1 to infinity. So telling whether something's increasing or decreasing is fairly logical. Like it's increasing, it means it's going up. Decreasing means it's going down. Boundedness and extrema. So when we have a function that is increasing and then decreasing, say like that, this has an upper bound to it. It has the highest thing it's going to be. And that's where it changes from increasing to decreasing. Bounded below would be something like, it could be a like a y equals x squared parabola. It's bounded below. It's not going below this value. But it could be something that's even weirder. Like we could have something like that where it's not getting below that value. Upper bounds or bounded above means it's not getting above that upper value. So like here, that would have an upper bound. And so it just means it's above or below. And then bounded just means both, above and below. So that one is bounded because it's not going off to infinity either in the positives or in the negatives. So that's what bounded is. And then extrema. Extrema is plural for extreme, and extreme means maximums and minimums. We have local extrema, and we have absolute or global extrema, and that would be maximums and minimums. So a local, if we had, let me draw a graph really quick. That went a little bit longer than I thought. So local extrema. A local maximum is going to be any point that is like the top of a hill, where everything around it is less than that. That's the local maximum. The absolute or global maximum is just the highest point. It's that one. There's only one. Local, there could be a whole bunch, but global, there's only one. And then minima, same thing. For local, it's all these little bottom points. And so that's going to be the local there. And then the absolute minimum, there isn't one because it keeps going off in the negative direction. So in this case, we do not have an absolute minimum. A line or a cubic function has neither an absolute minimum or absolute maximum. It may have local minimums and maximums there, depending on whether it swoops back down or if it just keeps going up, but it will not have any absolute maxima or minima. Asymptotes. We have two types of asymptotes. The first type are vertical asymptotes. These happen when you are dividing by 0. That's what gets us a vertical asymptote. And what it looks like, let's say we have y equals 1 over x minus 2. So we could plug in some points. We could plug in 0. We'd have 1 over negative 2. That's negative 1/2. We could plug in 1. We'd have 1 over negative 1. So that's negative 1. We could plug in 2. We'd have 1 over 0, which is undefined. That's our asymptote. And then we could plug in 3. 1 over 1, which is 1. So to graph these, we know that we have an asymptote at 2. So I generally put a dotted line so I remember it's there. And then we can plug in some points. So let's see, when x equaled 0, it was negative 1/2. When x equaled 1, it was negative 1/2 is down here. Then negative 1. And then it keeps going. And we have another asymptote there, but we'll get there in just a second. And then if we plug in bigger ones, we're going to get this one. So those are vertical asymptotes. It's when we divide by 0. Horizontal asymptotes and end behavior come not from dividing by 0, but it comes from the equation itself, generally speaking. Usually when you're looking at horizontal asymptotes and end behavior, you are looking at something with a big old fraction in it. So you have like f of x equals g of x over h of x. And so where g of x and h of x are both going to be just polynomials or functions. So what we're going to see here with our horizontal asymptotes is that we will have a horizontal asymptote at 0 if the degree of h of x is bigger than the degree of g of x. So what happens here is the denominator could be squared and the numerator is a linear function. The denominator is going to increase so fast that the numerator isn't going to even make a difference anymore. So that's if the degree is bigger that way. If the degrees are equal, if degree of h of x equals degree of g of x, then the horizontal asymptote is y equals the leading coefficient of h of x over the leading coefficient of g of x. So if we had something like, say, this one over here, the degree of the top is 0, the degree of the bottom is 1, so we end up with 0. That is how I knew that these would have asymptotes there and they wouldn't cross over the 0. If we wanted one where they were the same, let's say that f of x equals 3x squared plus 7 over 5x squared minus 9x. The degrees are the same, they're both 2. So we're just looking at this part, the x squareds can actually go away, and our limit is 3/5, and limit the horizontal asymptote y equals 3/5. Later on, we'll learn about limits, and they're the exact same thing. So that's that. And then if the degree, sorry, we're missing one. If the degree of h of x is bigger than the degree of g of x, then there's no horizontal asymptote. What happens there is that the functions go to infinity. So it could have something looks like that and like that. So there'd be no horizontal asymptote because they go to infinity. There's no oblique asymptote, which is a diagonal one, but we don't need to talk about that. Not yet, at least. So